You're listening to The Conversation.
Flight attendants, please prepare for a minute.
It's the 1960s and a new age of air travel is dawning. Flying is glamorous. People wear their Sunday best to travel, and the in-flight service is impeccable, even in economy class. They even use real knives and forks. Some airlines are thinking about going even higher, sending planes up into the stratosphere, more than 15 kilometers above the Earth, where they can travel even faster. In his lab in Washington, a Japanese scientist called Suki Manabe starts thinking. He's part of a brand new project at the US Weather Bureau, using computers to predict the weather and model the climate. And he wonders what would happen if lots of supersonic jets started flying high up in the stratosphere. What could it mean for temperatures on Earth? Manabe has also read studies warning about the increase in carbon dioxide emissions from burning fossil fuels, and so he plugs that into his model too. As the UN's annual climate summit continues in Brazil on the edge of the Amazon, this is the story of how climate models were invented. And this model of Manabe's, well, his findings, published in 1967, were voted the most influential climate change paper of all time. I'm Gemma Ware from The Conversation, an independent news and analysis platform partnering journalists with academics. Welcome to The Conversation Weekly, where experts explain how we ended up here. In today's episode, we look back at how these early climate models stood the test of time, but the very data sources that climate scientists around the world rely on to predict global warming are now under threat. Nada Jivanji, you're a physical scientist at the National Oceanic and Atmospheric Administration, or NOAA, in the US, where you study the physics of cloud, radiation, and climate. Welcome to the podcast.
Thank you. Great to be here.
So let's begin in the mid-1950s at the US Weather Bureau, which was located at that time in Washington, D.C., and it's just opened a new lab. Tell me about this lab and why it was set up.
Yeah, it was actually due to a proposal by John von Neumann, the famous mathematician and scientist who actually, in the late 40s and 50s, had pioneered the use of digital computers, and he had influenced the architecture of them and built some early prototypes in Princeton at the Institute for Advanced Study. And one of the projects that they had built the computer for was to try and do numerical weather prediction.
And who was funding the work on these early computers?
I believe a lot of the funding for this project, which required hiring all these engineers and computer programmers, came from what would have been called the War Department at the time. And I think the big motivations were being able to do calculations for the hydrogen bomb, for the next phase of nuclear weapons development after the war had ended, and then to also do weather prediction with potentially a particular eye for military applications. Could we predict the weather to facilitate military activity or even to alter the weather for military purposes? So then these methods were then taken up by the US Weather Bureau, which I think prior to that had been using, maps of pressure highs and pressure lows, and people who were trained to just look at these maps and predict what would come next just from experience.
When John von Neumann put together the proposal for this new lab using these computers to predict the weather, what was his bigger vision?
John von Neumann thought, in addition to predicting the weather on sort of timescales of a handful of days, it would be interesting to use these same computer models to actually do what he referred to as the infinite forecast, to keep predicting the weather in a self-consistent way over weeks and months and years, to then gather statistics about the weather. And these statistics of weather are what we call climate. What are the average temperatures in different seasons in different places? What kind of variability and weather and storms can you expect on average? So not specific forecasts, but the statistics of weather across the globe. And his original proposal is displayed in our laboratory, and he talks about all the interesting science and all the things that we would learn from studying this infinite forecast. And he charted that course and laid it out. And with this 4-page proposal, he submitted that, and it was accepted, and the laboratory was founded and originally housed as part of the US Weather Bureau in the DC area.
So this is really the birth of climate science as we know it today, is it?
It is the birth of modern climate science. That's right. And of course, there were climate scientists before this, but the methods they were using and the questions they were able to ask and answer were really quite primitive compared to what we're able to do now.
The first director of the lab, which came to be known as the Geophysical Fluid Dynamics Lab, and where you now work today, was a man called Joe Smagorinsky, who'd actually worked with John von Neumann as a junior scientist on those early computers. And then in 1959, Smagorinsky decided to hire a Japanese scientist called Sukuru or Suki Manabe. Tell us about Suki and what he was brought to the lab to do.
Yes. So Joe Smagorinsky recruited him from Japan. And I think post-war Japan was a very tough place to find a job. And so Suki was willing to come abroad. Joe understood that the first thing that needed to happen in a real climate model, or to do the infinite forecast, is you'd have to be able to model how energy was getting in and out of the climate system. If you're just going to do a couple of days forecast, then the fact that the sun is heating up the surface, and then the surface is heating up the rest of the atmosphere, and then the atmosphere is emitting thermal or infrared radiation to space, this whole energy balance is not so important. But if you were going to do an infinite forecast and to have it be consistent, you had to get that right. And so that was Suki's first assignment, was to build a computer program that could model that. That is the greenhouse effect.
What kind of person is Suki?
He's still around. He's quite old. He's not super active at the moment, but even into his late 80s and 90s, he was very active. So the lab where I work, the Geophysical Fluid Dynamics Laboratory, is located in Princeton. Joe moved it there several years after it started in Washington. And Suki was a professor emeritus there. And in my early years at GFDL, he would still show up to the seminars. He would sit in the very first row. He'd be the only person in the front row. And he'd be just paying rapt attention to whatever talk was happening. And then as soon as the talk ended, his hand shot up. He was super energetic. He wasn't afraid to ask a tough question or kind of get in the speaker's face, not in a combative or antagonistic way, because he actually seemed to be a very joyful person, but he was just so engaged. So he just wanted to know, why did the speaker do it that way? Why didn't they do it this other way? And I think that energy and vigor and just engagement and love and enthusiasm for the subject was something that he always had. And you can see that in his publication record, that he was just tireless. He was always on to the next thing. And I could perceive that energy even meeting him in his 80s.
So his first assignment was to model the greenhouse effect. How did he do that? What kind of model did he build to go about doing that?
Yeah, so this radiative transfer of energy, which these greenhouse gas molecules impact, is really something that happens in the vertical as energy travels from the surface and lower down in the atmosphere out to space. So what he started with were just single column calculations where it was only the vertical dimension of space was represented. And he put in these greenhouse gases and also put in sunlight and then just modeled how this radiative energy traveled up and down in this column.
Was that revolutionary to do that at the time?
People had done this kind of thing by hand before, but it was very laborious. And with a computer, he could really put in all the gases, CO2, water vapor, and ozone. So he could model how they overlap, which was important. And then he could run these calculations many times for many different parts of the atmosphere. And actually, one of the first things he did was kind of model the stratosphere. The part of the atmosphere that we live in and the part that has weather is referred to as the troposphere. And that goes up to about 15 kilometers, 40,000 feet. But then the layer of atmosphere above it is called the stratosphere. And that extends from about 15 kilometers to about 50 kilometers. So not all the way into outer space, but pretty close. And in that region of the atmosphere, you don't have weather. And so the temperatures there are really just determined by this radiative transfer, by this interaction of sunlight and infrared radiation with these greenhouse gases. And he was modeling how the stratosphere looks at different latitudes, because the stratosphere looks different in the tropics than it does, say, more towards the poles. And you could see him trying to model that using these one-dimensional calculations and actually doing pretty well, and gaining an appreciation for how little changes in the concentration of CO2 or of ozone could have a big impact on the stratospheric temperatures.
During the 1960s then, Suki began playing around with this new computer model to see what it could tell us about the sensitivity of the climate. Now there, can you walk me through the science of what he was trying to do?
In order to really make a prediction about climate, he somehow had to account for the fact that the surface transfers energy to the atmosphere, not just by radiation, but also by convection, where air masses close to the surface take heat and moisture from the surface, say that's evaporated off the ocean, and they lift that upwards, and that upward motion of fluid eventually creates clouds and thunderstorms and mid-latitude storms, and that's how the surface energy is transferred to the atmosphere. And then the greenhouse gas molecules take that energy and then send it out to space. So this convection, this overturning in the lower atmosphere was a key part of the whole energy cycle of the planet. And Manabe knew that he needed to model that somehow. And so in papers in 1964, and then most famously in 1967, he figured out a very simple way, something he called the convective adjustment, to put this into his model so that he had this actually really comprehensive treatment of the radiation, and then a simplified treatment of convection that, even though it was simple, it did exactly what it needed to do to model Earth's climate in this simple sort of one-dimensional setting.
And he made a prediction about CO2 emissions, didn't he? What did he predict back then?
He did. So he put this model together, and this model would predict the surface temperature. And then once he had this model, he said, well, I've got all these external things I had to feed into the model, like all these greenhouse gas concentrations. What happens if I change them? And so he just started changing things one at a time in his model. So for instance, he changed the stratospheric water vapor concentrations, because at the time, people were thinking about supersonic air travel, right? These Concorde jets that would fly in the stratosphere, but they would release water vapor in the stratosphere, and there was some concern that this might impact the properties of the stratosphere. So he checked that. He checked the sensitivity to ozone, and then he checked the sensitivity to CO2, because he was aware that even though at that point we were barely starting to measure the CO2 concentration in the atmosphere, he was aware that some scientists had speculated decades prior that burning of fossil fuels could increase CO2 in the atmosphere. So he thought this would be interesting to check. But it's not the main focus of that 67 paper. It was just one of the parameters whose sensitivity he was testing. He doubled it and I think halved it just to see. And he found that the surface and lower atmosphere warmed by about 2 to 3 degrees Celsius per doubling, depending on specific assumptions that he made.
Just so I understand it, was he predicting a doubling from where he was in the 60s, or was he already thinking about this idea that we now refer to doubling of CO2 emissions since pre-industrial levels?
He actually used a value which was slightly larger than what we know as pre-industrial, although at that time, interesting, we didn't know what the pre-industrial values were. That only came in the 1980s when we were able to extract that from ice cores. So that may have been his best guess as to what the pre-industrial concentration was.
Okay, but he was still really trying to think about this idea of fossil fuels and what burning more of them would do to our atmosphere. And what you're saying is he essentially got that right, and it's a prediction that's held up.
I believe that was his motivation. And yes, it is held up. And I think the fact that it is held up and the various ways that he constructed his model, these are the kind of assumptions that he made that have just totally stood the test of time. And they're why his estimate has quantitatively held up. And I think it was for these insights and this model for which he was largely awarded the Nobel Prize.
Suki Manabe is taking home the Nobel Prize for Physics for his work on climate change.
Coming up, more early climate predictions that have been proved right, and why the very data climate scientists rely on to make climate models now is under threat.
Hi, I'm Anna Walker, host of a new podcast called Jane Austen's Paper Trail from The Conversation. From a scandal-filled bun shop in Bath to a windswept walk along the Cobb in Lyme Regis, and even a glittering Regency ball, we've travelled around England to bring Jane Austen's world to life through interviews with today's foremost Austen experts. Listen to Jane Austen's Paper Trail wherever you get your podcasts.
Welcome back. This paper that Suki Manabe published in 1967 has now been dubbed the most important paper in climate science history. Alongside his prediction that doubling CO2 emissions would double the temperature of the surface and the lower atmosphere by a few degrees Celsius, Manabe also made a prediction that the stratosphere above that would actually cool. Talk me through what he found there.
This was actually surprising. I think he expected the surface and lower atmosphere to warm, but then he found that the stratosphere cooled. And it's because he had been so careful about his treatment of the greenhouse gases and the radiative transfer that he got this right. He saw a cooling of the stratosphere, he believed his model, and so he took that seriously.
On the stratospheric cooling, can you explain why it matters? Why is it important in countering arguments from climate skeptics that CO2 isn't causing climate change?
So the fact that you see the stratosphere cooling means that CO2 is having the effect that we think it is on the atmosphere. So basically, when you increase CO2 in the atmosphere, two things happen. You trap more radiation close to the surface, but then you actually emit more radiation from the stratosphere. But the stratosphere is cold. And so the radiation you're trapping near the surface outweighs the extra radiation emitted from the stratosphere, so it's a net trapping of heat in the atmosphere, and that's what causes global warming. But it's distributed between these two places, and it's actually the residual of these two effects. So the fact that you can see the cooling of the stratosphere is confirmation that this picture is correct, and that we're actually seeing both sides of the coin, not just the warming near the surface, but the cooling near the stratosphere. And so if this warming from the surface was coming from something else, from El Nino, or maybe the sun has gotten a bit brighter, something like that, we wouldn't be as likely to see this cooling of the stratosphere at the same time.
Okay, so we've got predictions about the atmosphere warming and the stratosphere cooling. From there, Manabe and his colleagues went on to make 3 more important predictions over the next few decades that have since come true. Can you walk me through those and why they're so significant?
So in 1975, he had a configuration of the model that, if I remember correctly, had just a slab ocean and only simulated a sector of the globe. This model was so primitive, and yet it showed 2 things that have stood the test of time. One was that, again, you saw stratospheric cooling, but now across all latitudes. And so this kind of confirmed his earlier 1D results. What he also found is that the polar regions in his model warmed more than the tropical regions, or warmed more than the global average. This phenomenon has become known as Arctic or polar amplification, and it has become a hallmark of climate change, and it is just ubiquitous across our field. You can see it in the present-day observations, you can see it in the paleoclimate record, and you see it in essentially all global warming simulations that are CO2 driven. A little bit later on, Manabe and Kirk-Bryan put together more comprehensive models with more realistic continental geography and with a full ocean. And when they ran those models, they found 2 more things. One is that when you increase CO2 and the globe warms, the land actually warms more than the ocean by a factor of about 1.5. And this matters for people, right? If you say there's going to be a degree of global warming, it's actually 1.5 degrees on land. So that's something I think people should know. And then the other thing, which is a little bit esoteric, but again is sort of further proof that our models were doing something right and that we understand the changes we're seeing in our planet. This 5th forecast is that warming over the Southern Ocean, the ocean that goes around Antarctica, that warming there is delayed. And that's something that Manabe predicted, that the rest of the globe warms, but this Southern Ocean, this remote, forbidding region that's very stormy, and there's all these stories about, intrepid Antarctic explorers braving the roaring 40s and 50s of latitude in the Southern Ocean. So it's not a place that most of us think about, but it turns out that when you simulate global warming, that part of the ocean doesn't warm, and that's just what we've seen in the observations.
As a climate scientist working today in 2025, do you look back at those early models and recognize what he was doing then? Or have our models today moved on so much that there's really no comparison?
It's such a good question, and the answer is yes and no. So Manabe himself, once he developed his 1D model, he didn't stop there. So he moved on to developing more comprehensive models. And yes, then today's climate scientists continued on this track where we now have global models simulating the globe at unprecedented resolution, sometimes even down to the kilometer scale. And we've got the plants and the vegetation and the carbon cycle and the aerosols. There's so much detail. And so in some sense, we've actually just gone light years beyond what Manabe was doing in 1967. At the same time, and this is work I've personally been involved with, we've actually also gone back to Manabe's models, his one-dimensional representation of the atmosphere. And we've asked ourselves, if we bring our best and updated knowledge about greenhouse gases and redo the radiation calculation, what do we get? And we get basically the same numbers. And so on the one hand, we've gone way beyond Manabe in the decades since. And on the other hand, some of those insights were so deep that we keep coming back to them, to deepening our understanding.
So all models have limitations. They're models. What does the accuracy of these early climate models, these early climate predictions, mean for climate science today, in your view? Why is it important that they were proven to be right?
Models are models. They're always things that they don't do well. This famous aphorism that all models are wrong, but some are useful. And today's models certainly have their shortcomings. If you ask climate models, what is going to be the regional climate change, at 2100 under a certain scenario, a certain part of the globe, how is precipitation going to change? How are droughts and floods going to change? Models don't always have great answers to that. And sometimes folks who are skeptical of climate science, for whatever reason, point this out as a means of casting doubt on climate science. And so that's what happened in this recent DOE report on climate science.
85 veteran researchers issuing a joint rebuttal after the Energy Department painted climate change as potentially beneficial.
So this was a report from the US Department of Energy.
Correct.
Published by the US government.
Yes.
Which has put climate skepticism right at the forefront of the Trump administration's response to environmental challenges.
Correct. And there's a lot in that report, but one of the things they do is they point out all these shortcomings of models. And there are kernels of truth in some of what they say. But the thing that was missing from the DOE report, it was just an emphasis on the uncertainties and on the things that the models don't do well. There was very little mention of all the things we do know and all the things that models do well and have done well for decades. And so I just felt that for a balanced narrative, we have to be able to point to the things that we know are true and the things that models have gotten right for a long time now, and in fact predicted before the observations came in. And so these uncertainties in climate models, be it as they may, are no reason to discount the warming that we're seeing, its impacts on humans and society, and everything else that present-day climate science is telling us.
There's a danger in this moment that we're in that even the ability of scientists like you to do this modelling going forward is under threat. The department that you work in, NOAA, and particularly the GFDL, it's been the subject of cuts from the Trump administration in recent months.
Hundreds of staff have been laid off at NOAA, the National Oceanic and Atmospheric Administration.
And I think some of your colleagues have been let go. How concerned are you about that and the ability of you and your scientist colleagues to keep doing that work?
We're all concerned about it. There were cuts, people were fired. Our ability to travel to conferences and publish papers was curtailed. And we all do this work because we believe in its importance. And it's the idea that the work isn't necessarily valued by the present government, or that we wouldn't be able to do it, or that somehow our lab and the models that it produces and all the science that comes out of it will be curtailed or shut is alarming.
And also, I guess, the ability to collect the data, because there's threats to even the databases and some of what you use to create your model.
There are, and climate monitoring is just a vast enterprise. Satellite observations, in situ observations, weather station networks, ocean floats, and those are all threatened to different degrees. The weather stations, I believe, will stay up because we're still interested in predicting the weather. But the satellites that are measuring the imbalance of radiation at the top of Earth's atmosphere, those are threatened. The floats that are monitoring ocean temperatures, especially in the interior of the ocean, because that's where the heat from global warming is being sequestered, those are potentially under threat. Even the monitoring of CO2 measurements around the globe, those are all under threat. And I know there's efforts underway to try and preserve them, but yeah, it's a very uncertain and unstable time for our field right now.
Well, thank you very much for explaining the history of it and why that history is important for understanding where we are now.
Yeah, it was a pleasure. Thank you.
That's it for this week's episode of The Conversation Weekly. You can read more on the conversation about the COP30 Global Climate Summit happening in Belém in Brazil, and we'll put some links for further reading in our show notes. This episode was produced by Katie Flood, Mend Marawani and me, Gemma Ware, with mixing by Eleanor Brezzi and theme music by Nita Saal. If you'd like to get in touch with us, you can email us directly at podcast@theconversation.com. You can sign up too for The Conversation's free daily newsletter by clicking on the link in our show notes. The Conversation is a non-profit news outlet dedicated to sharing the work of academic experts with a wider audience. If you like what we do, please do consider supporting us at donate.theconversation.com. That's donate.theconversation.com. And please do rate and review the podcast wherever you follow us. Thanks for listening.
Every week, Michelle Grattan offers you a ringside seat to the latest in Australian politics with interviews and insights from political insiders. On The Conversation's Politics with Michelle Grattan podcast, we cut through the spin and get to the substance with independent analysis of the issues that really matter. Stay informed, search and follow Politics with Michelle Grattan wherever you get your podcasts.